Okay, Monday morning, let's begin. Next couple of weeks will be a little bit slow, not really challenging, but I really like to see you to generate some feel when you face the problem to compute the structure reliability factor or reliability or central safety factor, vice versa. And we started working on the deterministic actual stress, and also the resistance or strength is the deterministic situation. We started, then on the way to finish the uniform probability function for the actual stress situations. Then we stopped in the middle. Then you presented the bi-weekly project, and which I really enjoyed. And we're going to continue for that mode. Then after we finish that, I call the random and the deterministic. Then we're going to look into also deterministic and random situation. Then lastly, fully random. Computational process for that is rather simple, straightforward, because it has the variable. But even if you have a structure system, you can really still use this the variable, the cases, because as you are doing, I think, or you have done, when you're looking into the stress situation, at the critical point, you can compute, of course, stresses and the relevant strengths. Then that's a two parameter situations. Then you can still use it. Then you have to really end up to get the right probability model for the loading situation. Sometimes the structure or resisting strength is pretty random, or could be a deterministic. Then it will be done this week. Then you can really get the feel, and you can really can get the rough answer. That's the clue. Get the feel of it. If you don't have a feel of it, saying, "Oh, I have to compute all the way down to the end," then a lot of things defeat yourself. Because after you compute that, oh, this is that, but you could really start from the beginning, get the feel, then get the ideas and the things like that. Okay. In this case, we're gonna look at the random. Random sigma s is actual stress or applied stress as a result of your analysis, and the deterministic, which we use as sigma r. This is the situations, okay? Well, this is general situation. Oh, I'm sorry. This is deterministic. So deterministic is we use yield. This is actual stress. We use unit has to be same. If you use input as a stress, output, let's say strength has to be the stresses. So this is the resisting. I use resisting. I use a yield, right? Yield the stress. Wow, yeah. So yield the stress deterministic, so I use sigma y. So now first the thing we have to do is to get the reliability computation, then you have to cast into probabilistic. Then it's a deterministic, this is random. The first step we did was, not the step, first case was uniform. Probability model. Probability model. So when you get to, if I draw the function, which is fs, f sigma s, I use sigma, capital sigma as a random variable. So this could be sigma like this, sigma. Then the uniform probability density function is like this, right? Uniform probability density function. So I use, let's say, this is lower limit, this is upper limit. This is a kind of the simplest probability model used quite often. And this area has to be equal to 1. Then this height is supposed to be what? 1 over sigma u minus sigma L. That's what we did. And cumulative probability distribution function, or simply distribution function, right here, let's say this is f sigma s. Before it gets to sigma L, of course, is 0. Then right here, cumulative value is equal to 1. Between is like this, right? So it's gonna be like that. That's what we have done it. Cumulative distribution function for the uniform situation. So that's what we have done it. So here, reliability is concerned is probability. What is it? Probability, maybe start from Jungan. What's this? The reliability is concerned, and in this case it's a structural reliability, is probability such that in terms of this and that, sigma s, sigma y, the probability such that the actual stress is less than equal to the yield stress. And this is deterministic, and this is random. We use capital letter, right? So that's the situation. So we have a model here for this. And sigma y is yield stress is concerned, is deterministic, means you have only one single value, right? So if I cast into the cumulative, the distribution function, it's going to be simply, we have done this, but I quickly review. This is S, and sigma y. So for the when you have a deterministic resisting strengths, or in this case we use as yield stress, it's much of course simpler. So this is kind of a reliability here. So first the model in general, I can say F exactly shown here. So I can say this equation here is simply sigma u minus sigma L, and sigma, any value here is a sigma, and a sigma L. This case, beyond the sigma u, below the sigma L is meaningless. Everything is zero. For the probability density function is concerned, up is 1, down 0. So here I can say sigma L, range is very clear between the range, and below 0, all otherwise region is all equal to, oh, I'm sorry. In this case, it's not the probability density function. So it's a 0 if sigma is less than equal to sigma L. Other case, when sigma is larger than sigma u, then you can cast from this simple model. In this case, this is, if this is a y, then this guy is a y, and so this is a valid zone. Sigma y, this is sigma y, things like that. That's what we have done last week, Wednesday last week. Deterministic, the yield stresses. Okay, the mean, the couple parameters, probabilistic parameters, is important. In this case, it's like a mean and standard deviations is what. So mean and standard deviation, sigma s, is equal to, in the equation form, Aline, what's the equation form for this? What's the limit? Minus infinity? Louder. Okay. Louder. S? What's this here? S? Because this is integration parameters, so you can just use S or T, whatever. But here, this usually, in this situation, what do you have? Anybody? Minus infinity. In this model here, you intend. You want? This is. This should be really sigma L, right? What this would be? What this would be? Where is that equation is 1 over sigma u minus sigma L, right? That's about it. Straight integration, right? So if you do that, then you have 1 over half sigma u plus this. I'm not sure whether I should give you midterm exam next Friday next week. Friday next week, our lab and Professor Han's lab, we are going down to Mexico for one-day meeting. So I don't want to give you exam when I'm away. So otherwise, I have to ask someone else to supervise it. But what I'm thinking is to give you the Friday in the first week of November. Any objection, any problem? Doesn't make any difference when I give you. I want to give you, I'm thinking to give a closed book exam to really see whether you really understand the basics. You have done some probability theory, some courses you took already. That doesn't mean that you really understood the structure, reliability, relevant. So that's what I'm thinking. November, first Friday of November, a closed book exam. How's that? Because everybody always, everything is in the book, who cares? I don't have to study until that moment, but that may be a good idea. And the variance, next one is variance. The variance, because I use a sigma, so I'm going to just use it here as a variance of sigma s is 1 over 12 sigma u minus sigma L square. I just going to put down just the result that you can derive such an easy one yourself. And sigma, believe it or not, try to derive all this. It's rather simple. U minus sigma L, you can variance sigma s, right, straight right from here. And you can express sigma L as these relations. Sigma S. All this notation is clear to you, right? And sigma, you derive this yourself. Shouldn't take more than, everything here shouldn't take more than something like 15 to 30 minutes. So. Then R can be expressed as, oh, okay. I'm gonna, what this means here? This means, right? This is meaning of same here, right? This is identical, right? Which is equal to the reliability, right? So yes, yes. This is reliability, right? Structural reliability for this particular situations. R is deterministic. Very, very good quality the materials. Whether it's a steel or aluminum whatsoever. Aluminum usually they don't have a yield stress. Okay, as I mentioned, aluminum doesn't have a yield. It just goes like this and breaks off. But steel has straight up has a yield stress, yield point. R is sigma y. This is a deterministic value. Sigma y. Yield stress is deterministic. Okay, it's a one single point, and minus mu sigma s plus 3 the variance of e to the s 2 times 3 variance. The beauty for these two parameters as a load and resistance model has a closed form solution. As I recall, all of them is closed form solution. Maybe some in the downstream to random situation, maybe not, but very nice forms. And the mu sigma s, what's the mu stands for? What's the mu stands for? Who cares? Shingyu. Mu, is it called the mu, not the, what do you call this? This is mu, what do you, oh, this is, oh, you're great, yeah. You? Is coefficient of variation, right? Coefficient of variation is a measure of what? 1. What does it mean? Sigma over mean. Normalize the dispersion, uncertainty. This case is input, which is really the actual the stress. So this case is the standard deviation. You have to be careful. I'm sometimes confused because I want to follow the Isaac's notation. So sigma, if I write this, makes sense? Do I have to write again here? Sigma S? I'm not sure what they use a variance, square root of the variance. That's what Isaac uses. Because square root of the variance is a sigma standard deviation. So then use S and e to the sigma S, right? Nu. Then now most compact N1 minus 1 plus 3 square root of 3 nu sigma S 2 square root of 3 sigma S. So this is, you can divide this guy divided by e to the mu, the sigma S, then that's N1. Then this guy is same as that, this is a 1, vice versa. You can have the equation equivalent. This is really same. You can compute the reliability. So over here is really relation. This is reliability, and this is a safety factor. The safety factor N1 is a central safety factor. This is a central safety factor, which is equal to what's over what? Just remember R over S would be easy. Simply that, resistance over the stress. This is what, but it's a central. Central means E to the R over E, God bless you, E to the S is equal to, for this case, is sigma, don't confuse it, this is yield stress, right? Yield stress over, this is mu S situation. Because resistance is one number, single value. Then this N1, remember this N1 is the central safety factor. It's a ratio of the mean. So when you say in the usual ship construction manual, building construction manual, they could talk about the N1, then you can convert into the reliability of the system. What the corresponding, remember, this is based on what probability model? Uniform probability model for the actual stresses. So you can just rewrite that as N1 is equal to this R here, I use small r rather than capital R in such a relation here is, this is really specific or required the reliability. In other words, let's say 0.9999. Okay, that's the required, the reliability. Then what kind of safety factor does it require? So it's a straight, the N1, the central safety factor versus the reliability of the system. This is rather simple. I could, I hate to say exam, but you usually say, what kind of the problem you're gonna give us very comprehensive questions I usually ask. For example, actual stress is random. And random, but follow, let's say, normal distribution. And the yield stress is, let's say, deterministic. Then find expression for the reliability. So you can derive simply. Now follow just the basic theory. You can do that. And the case 2, we're going to look at is sigma s, of course, is random exponential function. Very useful probability function. Exponential, the probability model. And of course, sigma r is deterministic. Sigma r. Exponential model. For the exponential model, this is not working now. F sigma s. We deal with the stress. Usual notation you are using. Stresses are sigma. That's the reason Isaac using the sigma to represent stresses. This is equal to a to the e to the minus a sigma. For sigma greater or equal to 0. We, in the previous chapter section, I use a different notation. I use a lambda rather than a, or sometimes I use 1 over theta as a, but that's immaterial. So now people just use the parameters. So this is otherwise when sigma is less than 0, then probability density function is equal to 0. So now then again the distribution functions you can just integrate to get this. So probability sigma s less than equal to sigma is equal to 1 minus exponential function minus AU a sigma. But over here it just added the capital U. Capital U is a step function. Capital U is a step function such that sigma, this is U, is like this. This is 0. And this is value of 1. Below 0 is 0. So by putting this, this is always that value when sigma is greater and equal to 0. This is really same as saying that this is 1 minus exp minus a sigma, then saying that sigma 0, identical format. Okay, U is a step function. Got it? You can just use this rather than this. There's no differences at all. So when you do this, then of course when you change this, well, if I just put this guy as R, in this case is special case, F sigma S, correct? This is correct? No? Correct or not? Correct. So which means over here I can just switch it. If you put Y here, then I can put Y there, and sigma Y there, vice versa, then R. You can rewrite identical format. So e to the 2 parameter, important parameter, sigma s is 1 over a. You can derive it. And the variance of sigma s is a variance, okay? Standard deviation square is equal to 1 over a square. Then you can derive this guy, derive that guy. And coefficient of variation sigma s is equal to 1 over a. 1 over a is equal to 1. Everything has to be there. Reliability expression for deterministic yield stress is rather simple, which is right there, is equal to 1 minus exp minus a sigma y mu sigma y. This is about all for the exponential distribution. Or you can express this by changing. This is deterministic. Over here, A is equal to 1 over e to the s. Replace this guy by this. You can write this guy as 1 minus exp minus n1 u sigma. Yeah, this is not right. For the exponential distribution for actual stress, that's about it. Then just you can rewrite from this. This is R and N1 relationship. If you rewrite this guy, then this is equal to natural log 1 minus R. Nothing to memorize it. Nothing to memorize except the model, but you don't need to memorize the model itself. So this is the relation. I'm going to change this to R, saying that for specific reliability value, for specific, okay, how the N1 going to correlate. So this is another expression for uniform actual loading situations. Then you can compute here, for example, for R value, for the R value required or specific, what's the central safety factor? And R value for, just to get the field 0.9, this is a 2.302. To get the 0.999 reliability, then you have to have central safety factor is almost a 7. Extremely high. I have never seen the safety factor of factor of 7. For nuclear reactor design, I remember it's around 3. Factor of safety is about 3. But to get 99.9% reliability of the system, then equivalent safety factor is 7. That's amazingly high. So what you have to be careful is a probability model is very important. Probability model, exponential goes like this. So that relate directly. Okay, for reliability for the uniform distribution, I don't have tabulated. You can use the tabulated. So N1 versus R. You can do that. 0.9. What? 0.99. 0.999, then what the value would be? I don't have that number, but it goes like this. You can compare for that. Is it getting, has a pattern for R deterministic? You can just use the probability distribution function for the actual stress as is, then switch the sigma in that model by sigma y. You're all set to compute the reliability, strictly speaking. And another probability model which is popular for structure mechanics, probabilistic mechanics, is Rayleigh distribution. Rayleigh distribution, what's the shape of the Rayleigh distribution? You have done some project also. What's the shape? Is it like a normal? It has a skew in there, right? It has a skew for probability distribution. Is something like this for the Rayleigh. Some of you use a Rayleigh in your project, and used quite a bit in the probabilistic structure mechanics or dynamics, and I'm gonna do that right now, a few minutes. Then Wednesday I'm gonna do the normal and the log normal. I like log normal because it has all kind of the skewness, negative skew, positive skew, and very elegant expression. You can recast the log normal into the normal when you take a natural log, and flexibility is there. So that we're gonna do that this week sometime. Okay, Rayleigh distribution. Rayleigh. We start for this probability density model. For the deterministic R, or deterministic R means it's really the one single value of yield stress. If you have this, after that, if you generate this, then you can generate R. That's the procedure. Very easily in these situations. So this is equal to, again, this is Isaac's notation he happened to use, but previous section I use a different value, but it really doesn't matter. I use x rather than sigma, so in this case sigma has to be greater or equal to 0, otherwise 0, otherwise less than 0, otherwise is 0. Then for the cumulative distribution function, it has, I want you to, if you have a time, generate, just to derive this. But if you look at Isaac's book, of course any book has a slight error in there, when we find the error, I usually ask Higyu, he's my teaching assistant, ask to conform, so to doubly make sure it's correct. There is some error, but minor. So here, the reliability is concerned. Here is sigma s, sigma y. So it's readily available for this case only. So replace from here, readily available, replace sigma by sigma y. From here, you replace sigma by sigma y, then that goes right into it. Straight, very straight. 4. I'll stop right here. It's a little bit tedious, I know, but when resistance is deterministic, it's really simple. You can readily evaluate the vice versa. Okay. All right, so I'll continue the Wednesday. I want to finish this deterministic yield on Wednesday. Then we can go into different case on Friday. Okay.